previous lecture, we were discussing the notion of order of convergence of a sequence to measure how fast a sequence converges to its limit. In this lecture, we will start our discussion in a new topic called differential calculus for functions of several variables. You know, differential calculus is majorly dependent on one concept, that is limit. In our high school, we all have gone through the notion of limit for a function of one variable. We have gone through the notion limit extends to c if x for a given function of one variable f. Here in this lecture, we will discuss the corresponding notion of limit for function of several variables. In addition to the notion of limit for functions of several variables, we also will go through the notions of continuity. Uniform continuity and Lipschitz continuity are the topics of discussion in this lecture. In our high school, we all have gone through the notion of limit of a function of one variable, from where we are all familiar with the shorthand limit x tends to a of a function if x is equal to some value, say capital L. For a real valued one variable function f, this shorthand means that fx values come arbitrarily closer to the value capital L when the variable x is in a sufficiently close vicinity of the point A. For this to be meaningful, the function f must be well defined in the vicinity of the point A, and thus we consider that this point A is a limit point of the domain of definition of the function f. In mathematical language, this shorthand means that for any given epsilon greater than 0, there exists a delta greater than 0 such that the absolute difference between fx and L is less than epsilon whenever x is in delta neighborhood of the point A. Here, the points x's satisfying this inequality must be points inside the domain of definition of the function f. This inequality here essentially means that the value of the function f at x is lying in between L minus epsilon to L plus epsilon whenever the argument x is inside the open ball A minus delta to A plus delta, excluding the center of this open ball. Geometrically, this means that if we look at the graph of the function y is equal to fx, say this is the graph of the function y is equal to fx, and then we focus our attention in between L minus epsilon to L plus epsilon level, say this is the level of L minus epsilon and this is the level for function value y is equal to L plus epsilon, and here is the location of say capital L. The point A associated to this definition is, let's suppose, over here. Then this mathematical statement says that if we focus our attention in between L minus epsilon to L plus epsilon, then corresponding to the epsilon value, we will get a delta value, so that when x is inside A minus delta A plus delta, then the function values must be lying in between L minus epsilon to L plus epsilon. Here from this graph, we notice that corresponding to this chosen epsilon, the graph of the function y equals to fx falls inside L minus epsilon to L plus epsilon when the argument points x's are lying in between from here to this point. Now choose a delta greater than 0 so that A minus delta to A plus delta is lying in between this range, then you will find that for any point in between this a minus delta to a plus delta, the function values are all lying in between L minus epsilon to L plus epsilon. So for functions of one variable, this shorthand or this equality means that corresponding to a given arbitrary closeness measurement epsilon, for the function value fx and L, there must exist a delta greater than 0 such that as and when x is not more than delta distance away from a, fx value will be epsilon precise to the value capital L. For functions of several variables, the notion of limit is very similar to this one, that corresponding to any given precision measurement epsilon greater than 0, if we get a delta greater than 0 or radius as and when x is inside the delta radius ball of the point A, the fx value satisfies this inequality, then we say fx approaches to capital L when x tends to A. So for real valued several variable functions of, let's suppose, n variables, the definition of limit at a point A is exactly same as this one, just with an amendment that instead of absolute difference between x and a over here, we'll consider the distance between x and a with the help of a norm in the n-dimensional Euclidean space. Now here I would like to ask you a question that we all know for functions of one variable that limit at a point say A exists if the left hand limit and the right hand limit at the point A exist and they are equal, because in the real number line to approach towards A we have just two possible ways, either from the left or from the right. Now my question is, can we have such a result for a function of two or more variables? The answer to this question is negative, that such a result cannot be even thought for functions of two or more variables. Because if we simply consider a function of say two variables and the location of the point A is, let's suppose, somewhere over here, then we notice that to approach towards this point, we not only have this left hand or from right to the left way to move towards the point A, but we have infinitely many ways to reach at the point A, not only straight line paths but also we have even curvical paths to reach at the point A. And therefore such a result that left hand limit and right hand limit are existing and they are equal will not imply that the limit at the point A exists for functions of several variables. However, we can take an opportunity of this observation to certify non-existence of limit of a function of two or more variables. That if there exists two paths to reach at the point A, so that along these two paths the function approaches to two different limits L1 and L2, then the limit at this point does not exist. We may call it as a two-path test for non-existence of limit. It states that if there exist two paths along which the function values fx's approach to two different limits, then limit x tends to a if x does not exist. For example, the limit of the function x1 square into x2 over x1 to the power 4 plus x2 square at the point 0, 0 does not exist, because you consider two paths say x2 is equal to x1 square and say x2 is equal to 2x1 square, then you will find that along x2 is equal to x1 square, this limit reduces to limit x1 tends to 0, x1 to the power 4 in the numerator divided by 2x1 to the power 4 in the denominator, which is equal to half. But along x2 is equal to 2x1 square, this limit reduces to limit x1 tends to 0, 2x1 to the power 4 divided by 5x1 to the power 4, which is equal to 2 by 5, not equals to the limit half along the path x2 equals to x1 square, and hence this limit does not exist. Interestingly, you please note that this limit value is equal to 0 along any straight line path. Say x2 is equal to kx1 passing through the concerned point origin, but still the limit does not exist. So having same limit along all straight line paths approaching towards a given point does not necessarily assure that a limit exists at that particular point. Now next we will discuss the notion of continuity of a function of two or more variables. A function of several variables, say f, which is real valued, is called continuous at a point, say a, in the domain of definition of the function f if the capital L value inside this definition is equal to the functional value fa. That is, the function f is said to be continuous at the point a if for any given epsilon greater than 0 there exists a delta greater than 0 such that this inequality is happening to be true whenever norm of x minus a is less than delta. We neatly write this definition over here that if for any given epsilon greater than 0 there exists delta greater than 0 such that the difference between the function value and the function value at a is less than epsilon whenever norm of x minus a is less than delta. Immediately from this definition of continuity of a function f at a point a, we get a result that if the function value at a is greater than 0 and the function f is continuous at the point a, then there must exist a neighborhood of the point a, or there exists an open ball of radius delta greater than 0 such that the function values inside the neighborhood or open ball centering at a having radius delta is greater than 0. Here the points x's must be points of the domain of definition of the function f. This result says that if f is a continuous function that has function value positive at a point, then there must exist neighborhood of the point a in which the function values at all points in that neighborhood are all positive. This result is in fact true for negative values of the function as well. If fa is less than 0, then you will have a neighborhood of the point a in which the function values are all negative. This result is thus commonly known as sign preserving property of a continuous function, because we get a neighborhood of the point a in which the sign of the function values is that of the function value at the point a. This result is very simple to prove. It is really immediate from this inequality defining continuity at the point a. From this inequality of defining continuity at a, if we choose epsilon to be say half of fa or modulus fa, then we see that fx is lying in between fa minus epsilon to fa plus epsilon. So fx is bigger than fa minus epsilon for all x inside this delta radius ball, with x being a point in the domain of definition of f. That is, we get fx is greater than half fa, which is greater than 0, and this inequality is true for every x inside this delta radius open ball and inside the domain of f, which proves the result that we wanted. Well, now here goes the definition of continuity of a function at a given point a. If a function f is continuous at each and every point of a given subset, say capital A, of the domain of definition of the function f, then we call the function f is continuous on the set capital A. With the help of this definition of continuity of a function on a set, we will now define the notion of uniform continuity of a function. Before getting into the notion of uniform continuity, let me mention the sequential approach to identify continuity of a function, because the sequential approach will be quite often required throughout the course, which states that let A be a point inside the domain of definition of a function f, which is a function of several variables, and the point A is a limit point of the domain of definition of the function f. Then limit extends to a if x is equal to fa, if and only if for every sequence xk in the domain of definition of the function f that are converging to a, the corresponding sequence of real numbers fxk converges to the real number fa. The proof is a bit trivial, which is straightly followed from the definition of continuity of a function at the point a, and a detailed proof of this result can be found from the proof of the theorem 4.2 on page 84 of the famous book by Walter Rudin entitled Principles of Mathematical Analysis. Here I am keeping a home task that you please try to employ this result of sequential criterion of continuity to show that the function fx is equal to sin 1 upon x when x is not equal to 0, and 0 when x is equal to 0 is not continuous at the point x is equal to 0. To show this, that the function f is not continuous, you just try to identify two sequences xk and xk dash, both of which are converging to 0, but fxk and fxk dash, they are converging to two different limits. That will prove that the function f is not continuous at x is equal to a. Now we will discuss the notion of uniform continuity of a function. Let's suppose we have a function that is continuous on a subset of the domain of the function. Let us consider this set to be capital A, and the function f is continuous on the set capital A. That is, the function f is continuous at each and every point inside the set capital A. Let us suppose small a be a point in the set capital A. Then due to the definition of continuity of the function f at the point small a, for any given epsilon greater than 0, there exists a delta greater than 0 such that for any point x in the domain of the function f and satisfying norm x minus a less than delta, we have absolute difference between fx and fa lesser than epsilon. Now if we move our attention from small a to some other point, let's say a dash inside the set capital A, and keep the same epsilon fixed, then it may happen that the same delta does not work to realize these inequalities, and a smaller delta may be necessary for the point A dash to fulfill this requirement. For example, let's suppose if the graph of the function f is, say, this, here we are considering a function of one variable, and then let us take the point A is, let's suppose, somewhere over here, and A dash is somewhere over here. Then we fix our attention with a given epsilon, say epsilon greater than 0, and with this epsilon amount, let's suppose if a minus epsilon is here and if a plus epsilon is somewhere over here, that means epsilon length is this much, and with the same epsilon corresponding to if a dash, let's suppose if a dash minus epsilon is here, if a dash plus epsilon is here, and thus corresponding to the point A, the delta value must be such that a minus delta to a plus delta must be an interval in between this range, and the delta value or delta dash value corresponding to the point a dash must be such that the interval a dash minus delta dash to a dash plus delta dash must be lying inside this range. So from this figure we sense that when we alter our point A to A dash and keep the same epsilon fixed, this delta value gets altered to realize this inequality, and therefore this delta not only depends on the choice of epsilon but also on the point A at which we are checking out the continuity of the function. So in a erudite fashion, we commonly write delta as a function of not only of epsilon but also the concerned point A. Now here the function f is given to be continuous on the set capital A. Varying the point small a to a dash, the delta value gets varied from delta to delta dash. If we alter our attention from a dash to some other point, let's suppose a double dash, then we will have the corresponding delta double dash and so on. Now let us keep collecting all these delta values, delta, delta dash, delta double dash and so on, and try to figure out if we can find a common delta value that will uniformly work for every point small a inside the capital A. You may think of taking the minimum most value of all these delta, delta dash, delta double dash and so on, or rather try to figure out the infimum value of all these deltas corresponding to all small a inside the set capital A, and check if this delta naught is a positive quantity, so that this delta naught will work for all the points small a in capital A. But here you notice that all these delta epsilon a's are positive quantity, and hence this delta naught is certainly greater than equals to 0, but not necessarily always greater than 0. In case if delta naught is greater than 0, then we see that for this delta naught greater than 0, we get the observation that for all small a in capital A, we have norm x minus a less than delta naught implies fx minus fa, and its absolute value is less than epsilon. That is, the same delta works uniformly across all the points small a on capital A. In such a case, when delta naught is greater than 0, so we can just write this entire line by x1, x2 belonging to capital A with norm of x1, x2 less than delta implies if x1 minus fx2 absolute value is less than epsilon. And as this delta works uniformly across all the points in capital A for a given epsilon, the function f is called uniformly continuous on the set capital A. So for a uniformly continuous function f on a set capital A, this delta depends only on epsilon but not on A. So we neatly write the definition of uniform continuity as follows. Let capital A be a subset of domain of definition of f. The function f is said to be uniformly continuous on the set capital A if corresponding to any given epsilon greater than 0 there exists a delta which is dependent only on epsilon, such that for any pair of points x1, x2 whose distance is less than delta, we have absolute difference of fx1 and fx2 is less than epsilon. From this definition of uniform continuity, we immediately see that if we just fix our attention on a given point, say x2 is equal to some point C in capital A, then we have norm x1 minus C less than delta, implying absolute difference of fx1 and fc is less than epsilon, and hence the function f is continuous at the chosen point C inside the set capital A, and hence any uniform continuous function on a set capital A is certainly continuous on the set capital A. Let us now try to figure out the geometry behind this notion of uniform continuity. First, we will consider a function of one variable, and then we will generalize our observation for functions of several variables. Let the given function be f. In order to this function small f be uniformly continuous on a given set, say capital A, we need to have this entire line true, which for function of one variable reduces to for any pair of points x1, x2 being chosen from capital A and satisfying this norm to be replaced by absolute difference, that is modulus of x1 minus x2 less than delta, implies modulus of fx1 minus fx2 is less than epsilon. This entire implication is essentially saying that if x1 and fx2 have the maximum most distance less than epsilon whenever x1 and x2 are within maximum distance delta. Let us relate this observation in the graph of the function in the xy plane. Let's suppose this is the graph of the function y is equal to fx, and fix our attention with some specific point in the set capital A. Let's suppose we are fixing our attention with x2 to be equals to some point, say small c, inside the set capital A, and suppose the location of c is somewhere over here. Now we look at this inequality, which gives us the range c minus delta to c plus delta, and this inequality gives us the range fc minus epsilon to fc plus epsilon. Now at this point CFC, if we draw a rectangle with base slightly smaller than 2 delta and height slightly smaller than 2 epsilon, where the center of this rectangle is the concerned point CFC, then we'll find that this entire condition will imply the graph of y equals to fx in between c minus delta to c plus delta will lie completely within these two heights of the rectangle. That is, the graph of the function in between c minus delta to c plus delta does not pass through this top or this bottom side of this entire rectangle. Now we consider this rectangle having center at this point CFC to move from the point CFC to any other point, say over here, and check if the graph of the function in between c minus delta to c plus delta never cross the top and bottom side of the rectangle. And if we realize that this graph never crosses the top and bottom of this rectangle having fixed length of base slightly smaller than 2 delta and fixed height of length slightly smaller than 2 epsilon, then the function f must be an uniformly continuous function inside the set capital A. Here in this graph, the collection of points in capital A are starting from here to till the graph is ending over here. So neatly, you consider a rectangle having base slightly smaller than 2 delta, height slightly smaller than 2 epsilon, and having center at the points on the graph. Then you keep moving these rectangles on keeping center CFC on the graph of the function. And if you find that on all these rectangles, if the graph of the function y equals to fx never crosses the top and bottom side of the rectangle, then the function f is uniformly continuous. So essentially, a uniformly continuous function does not allow a sudden rapid change of the function value. If there exists a sudden rapid change of the function value, then obviously the graph of the function will cross either top or the bottom of this rectangle. Let us now consider one or two examples of uniform continuous functions. Consider, say, fx the function as x square, which is a function of one variable x, and let us check whether it is uniformly continuous on any bounded interval, in specific, let us say in the open interval a to b for some a greater than 0. In order to check the uniform continuity of this function f, we start with the expression of absolute difference of fx1 and fx2 for any pair of points x1 x2 in the given interval a to b. This expression is equal to modulus of x1 plus x2 times modulus of x1 minus x2. As x1 and x2 are inside this open interval a to b, so both the x1 and x2 are less than b, so we get this quantity strictly less than 2b times modulus x1 minus x2. So for any given epsilon greater than 0, we choose delta to be epsilon by 2b, which will then give us that modulus of x1 minus x2 less than delta and x1, x2 belonging to the open interval a to b, absolute value of fx1 minus fx2 is less than this 2b times modulus x1 minus x2, as modulus x1 minus x2 is less than delta and delta is epsilon by 2b, so we get here 2b times epsilon by 2b, and ultimately this absolute difference is less than epsilon, and hence the function f is uniformly continuous on the interval a to b. Now I would like to ask a question here. What if we consider the interval a to b to be unbounded, or specifically let us consider the interval say a to infinity, and let us find if the function f is uniformly continuous inside this unbounded interval or not. We see that when we have proved that the function f is uniformly continuous on this bounded interval, we used the value of delta to be epsilon by 2b. Now here if we keep on increasing the value of b, then this value of delta gets decreasing, and as b gets larger and larger, and ideally b tends to positive infinity, in that case this delta value tends to 0, and so there may not exist any delta greater than 0 which will work for any value of b greater than a, and hence possibly the function f is not uniformly continuous on this unbounded interval. So this is just a crude analysis of checking whether the function f is uniformly continuous on the unbounded interval a to infinity or not. For a mathematical or algebraic proof for non-uniform continuity of the function f on this unbounded interval, we proceed as follows. That we take say epsilon is equal to some number, say epsilon is equal to 1, and corresponding to this epsilon we will show that there does not exist any delta greater than 0 that will uniformly work for every possible points inside the interval a to infinity. We will specifically show then that for any delta greater than 0, we have 2 points x1 and x2 for which the distance between x1 and x2 is less than delta, but the distance between the function values fx1 and fx2 is bigger than epsilon. So we let epsilon is this quantity and take any delta greater than 0. Now we choose x1 to be say a plus 1 upon delta, and take x2 to be the point x1 plus delta by 2. Then we see that the distance between x1 and x2 is equal to delta by 2, which is less than delta, but this difference is equal to, you please calculate what is this expression, and so that this is 1 plus some positive quantity, and hence this is greater than epsilon, which proves that corresponding to this epsilon is equal to 1, you don't have any delta, for which for any pair of points x1 x2 with modulus of x1 minus x2 less than delta, we not necessarily have modulus of fx1 minus fx2 less than epsilon, and hence the function f is not uniformly continuous on the interval a to infinity. Now let me give you two home tasks that you please try to show that the function fx is equal to sin x is uniformly continuous on the entire real number line capital R. However, the function fx is equal to 1 over x is not uniformly continuous on the interval open 0 to infinity. From a geometrical inspection, you can quickly figure out why these two examples are going to give you an example of uniform continuity and another is not uniform continuity. For the function fx equals to sin x, you see that you don't have any sudden rapid change of the function value. For a given epsilon greater than 0, if you try to scan with a rectangle having height slightly smaller than 2 epsilon and keeping the center of the rectangle on the graph of the function and keep moving the center of this rectangle on the graph, and accordingly this rectangle will scan the entire graph of the function, you will find that the graph of the function fx equals to sin x will never cross this top and bottom of the rectangle if we consider a small enough delta value. However, for the function fx equals to 1 upon x, we see that there is a rapid change of the function when we move towards x is equal to 0, and therefore whatsoever smaller base of the rectangle you take, that the graph of the function fx equals to 1 upon x will certainly cross the top of this rectangle, and hence you will not be able to find a positive delta for which the graph of the function will never cross the top of the rectangle having base slightly smaller than 2 delta. So the function fx equals to 1 by x will not be a uniformly continuous function on this interval 0 to infinity. But this goes geometrical analysis of the given functions to check their uniform continuity. But I would request you to algebraically figure out the uniform continuity of these two functions. That means when you are showing that fx equals to 1 by x is not uniformly continuous, you please proceed in this manner, that you show us a specific value of epsilon for which there does not exist any delta greater than 0, with which the requirement of uniform continuity will be realized. That means for every delta greater than 0, you show us specifically with algebraic expression a pair of points x1 and x2 such that modulus of x1 minus x2 is less than delta, but modulus of fx1 minus fx2 is bigger than your chosen epsilon. Now here, while explaining the geometrical essence of the uniform continuity, I took off a function of one variable. But what would be the geometrical interpretation of uniform continuity for functions of several variables? In order to explain the geometry for functions of several variables, let me just consider a function of two variables and try to have a geometrical interpretation. Then by increasing the number of variables, we will get the geometrical interpretation for functions of three or more variables. Let's suppose we have a function of two variables x1 and x2, The graph of the function of two variable obviously is a surface in the three-dimensional space. Let's suppose the surface of z equals to f x1 x2 is this surface, and the condition of uniform continuity for function of two or more variables comes up with this portion as norm of x1 minus x2 less than delta. For functions of two variables, this inequality together with this inequality will give us a cylindrical region, a vertical cylinder having base of radius delta and height slightly smaller than 2 epsilon. So at each and every point on the surface of z equals to f x1 x2, we keep scanning with a cylinder of height slightly smaller than 2 epsilon and base radius is delta. Now you keep on scanning with this cylinder, placing the center of the cylinder on the surface of z equals to f x1 x2, and if you find that the surface never crosses the top and bottom of the cylinder, then the function z equals to f x1 x2 is uniformly continuous. Here obviously, while saying that this is a cylinder with circular base, I am keeping in mind that the norm that we have taken over here is the usual Euclidean norm or the Lebesgue norm. This usage of Lebesgue norm or Euclidean norm is a standing assumption throughout the entire course. Unless otherwise specified, we will consider only the usual Euclidean norm or the Lebesgue norm. If however, if you would have considered some other knob instead of the 2 norm over here, then just the shape of the base of this cylinder will get changed. But the entire phenomenon of checking uniform continuity through scanning with a cylinder will not get changed. Now you notice that not it is always possible for every function to check their uniform continuity with the very definition of uniform continuity, and therefore obviously we take help of some properties of uniform continuous functions that are necessarily satisfied by general uniform continuous functions, and hence if that necessary condition is not satisfied, the function will not be a uniform continuous function. Towards this, one fascinating result is that a uniformly continuous function necessarily maps a Cauchy sequence to a Cauchy sequence. Neatly, the result states that let capital A be a non-empty subset of the domain of definition of the function f, and the function f is a uniformly continuous function on the set capital A. Then if xk is a Cauchy sequence whose elements are in capital A, then the sequence of real numbers fxk is a Cauchy sequence. This result is although immediately followed from the definition of uniform continuity, because as the sequence xk is Cauchy, therefore you will have this inequality is true after certain index number k greater than or equals to k naught, which will then imply by this condition that the sequence fxk is a Cauchy sequence. You please try to write out on your own to prove this result. You may cross check your writing with the result proven in, say for instance, the book by Professor S.K. Mapa on real analysis. You may please visit the page number 298 of the book by Professor S.K. Mapa and Introduction to Real Analysis on its 10th edition. However, here in this book, this proof is given for a function of real variable, but from the proof you will get a sense whether your writing on the proof for functions of several variables is going correct or not. Now with the help of this result, you can immediately find that this function fx equals to 1 upon x is not uniformly continuous. You just take the sequence xk is equal to 1 upon k, which is a Cauchy sequence in this interval 0 to infinity, but the corresponding sequence fxk is not a Cauchy sequence. Let me also give you an example in which we will employ this result to check the uniform continuity of the given function. Say fx is equal to sine 1 upon x when x is not equal to 0 and 0 when x is equal to 0. Let us try to check the uniform continuity of this function f on the interval say open 0 to 1. For this function, you may try with taking the sequence xk is equal to say 2 by k pi, which is a Cauchy sequence inside this interval 0 to 1, but the sequence fxk is equal to sine k pi by 2, which is not a Cauchy sequence because of not being a convergent sequence of real numbers, and therefore this function f is not uniformly continuous on this interval open 0 to 1. Now I will mention a result on uniform continuity by Henrik Edward Heine and George Cantor, which is famously known as Heine-Cantor theorem, which says that continuity on a compact set implies uniform continuity. Neatly, the result states that let capital A be a compact subset of Rn and the function f is continuous on the set capital A, then the function f must be uniformly continuous on the set capital A. For a proof of this result, you may please visit a classical book on mathematical analysis by Apostol. You please visit the theorem number 4.47 on page 91 of the book entitled Mathematical Analysis by Tom M. Apostol. These mathematicians Heine and Cantor both are two famous German mathematicians, and this person Cantor is the person who is famously known for creating set theory in mathematics. These results for a function of one variable will then ensure us that if a function f is continuous on a closed and bounded interval a to b, then the function f must be uniformly continuous on the interval a to b. However, if the function f is continuous on an open interval or semi-open finite interval, then the function f might not be uniform continuous. For example, here you consider this function fx. This function is continuous on this open interval 0 to 1 but not uniformly continuous, and therefore continuity on a bounded interval may not necessarily imply uniform continuity, but continuity on a closed and bounded interval for a function of one variable will imply the function f is uniformly continuous on the concerned closed and bounded interval. However, regarding uniform continuity on a finite open interval, we have the following result, that let the function f is continuous on the interval open a to b, then the function f is uniformly continuous on open a to b if and only if the right hand limit of the function at a and the left hand limit of the function at b do exist. For a proof of this result, you may please visit the book of Professor S.K. Mapa, the theorem number 8.7.6 on the page number 300 in its sixth edition. For uniform continuity on unbounded intervals, we have the following result, that if f is continuous on closed 0 to infinity and limit extends to positive infinity, fx is equal to 0, then f must be uniformly continuous on the interval closed 0 to infinity. Similarly, if f is continuous on negative infinity to closed 0 and this limit extends to negative infinity, fx is equal to 0, then also the function f is uniformly continuous on minus infinity to closed 0. A proof of this result can also be found from the book of Professor S.K. Mapa. This book, you please figure out the page number so that if you flip the nearby pages of this result, you will get to know few more results or few more examples on checking uniform continuity of a function of one variable. Now next, we will move towards a stronger concept of uniform continuity, that is Lipschitz continuity. A function of several variables is called a Lipschitz continuous function on a non-empty subset of Rn, say capital S, if there exists a non-negative constant k such that for every pair of points x1 and x2 inside the set capital S, we have modulus of fx1 minus fx2 is less than or equal to k times norm x1 minus x2. This constant capital K is called a Lipschitz constant, and often we refer the function f is k Lipschitz continuous in order to emphasize the value of the constant k for which this inequality is satisfied. This notion of Lipschitz continuity is named after the German mathematician Rudolf O. S. Lipschitz, who was possibly the first person to consider this condition in the year of 1864 in his study on the convergence of the Fourier series of a periodic function. From this definition of Lipschitz continuity, it is immediate that if a function f is Lipschitz continuous on a set capital S, then the function f must be uniformly continuous on the set capital S. Because for a given epsilon greater than 0, we take delta to be epsilon divided by this constant k, for which we will realize that for any pair of points x1, x2 with norm of x1 minus x2 is less than delta will imply that modulus of fx1 minus fx2 is less than epsilon, and hence any Lipschitz continuous function is uniformly continuous. Now let us try to figure out a geometrical interpretation of Lipschitz continuity. At first, we consider a function of one variable to find a geometrical interpretation of Lipschitz continuity, and then we will generalize the interpretation for functions of several variables. Let us suppose the function f is Lipschitz continuous on a set, say capital S. Then for any pair of points, say a generic variable x and a point x bar inside the set capital S, we have modulus of fx minus fx bar less than or equals to some non-negative constant k times modulus x minus x bar, which is equivalent to if x lies in between fx bar minus k times modulus x minus x bar and fx bar plus k times modulus x minus x bar. That is, the graph of the function y is equal to fx lies in between the graphs of the functions y is equal to this left hand side expression and y is equal to this right hand side expression. Let us try to see the locations of the graphs corresponding to this left hand side expression and right hand side expression on the graph of the function y equals to fx. Let us suppose the graph of the function y is equal to fx on the xy plane is this hypothetical graph y is equal to fx, and suppose the location of the point x bar is somewhere over here and the associated point in the graph is this point whose coordinates are x bar and fx bar. Now this left hand side expression y is equal to fx bar minus k times modulus x minus x bar is a graph given by this one. Similarly, for the right hand side expression, we will have a graph, this one, having vertex at the point with coordinates x bar and fx bar. Now this inequality says that the graph of the function y equals to fx lies below this graph and above this graph. That means the graph of y equals to fx will entirely lie in this dotted region, and this observation has to happen for every point x bar. That means we keep shifting these two lines with slope minus k and k having intersection on the graph of the function, and these two intersecting lines form a double cone whose upper part is this red graph and lower part as this blue graph. Now keep shifting this double cone, keeping the vertex of the cone on the graph of the function. If you find that the graph of the function y equals to fx lies outside this cone, that is in this dotted region, then the function f is a Lipschitz function. Now this observation of keeping the graph of y equals to fx outside this cone is for a function of one variable. For functions of two or more variables, this inequality of Lipschitz continuity gets revised by norm on the right hand side, and hence in this inequality you will have on the left hand side here norm of x minus x bar, on the right hand side also norm of x minus x bar. Now if we consider our commonly used usual Euclidean norm, then you notice that this left hand side expression will give us a right circular inverted cone on the bottom, and the right hand side gives us a right circular cone at the top, and the graph or surface of the function y equals to fx must be lying outside this double cone having vertex at the point x bar fx bar. Here I have drawn this right circular double cone in the graph of a function of one variable, but in order to be more erudite, you please consider a function of two variables, let's suppose of x1 and x2. Then you draw the surface of y equals to f x1 x2. Then on the surface you please keep the vertex of this cone and check whether the surface of y equals to f x1 x2 lies outside this double cone or not. If yes, then the function f is Lipschitz continuous, otherwise not. We can also extract an interpretation of Lipschitz continuity immediately from this inequality, which tells that the ratio of modulus fx1 minus fx2 and norm x1 minus x2 is bounded by the constant capital K. Now we see that this left hand side expression gives us the average value change of the function due to the movement from x1 to the point x2. If we move ourselves from x1 to x2, the function value gets changed from fx1 to fx2, and hence this left hand side expression gives us the average value change of the function due to the movement from x1 to x2. And this entire inequality tells us that if the average value change of a function is bounded, then the function f must be Lipschitz. In order to check whether this average value change of the function f is bounded or not, we go for calculating maximum most value or the supremum value of this left hand side expression on the given set capital S and check if the supremum is finite and a definite quantity, then the function f is Lipschitz continuous on the set capital S. We also interestingly see that for a function of one variable, this expression gives us the absolute value of the slope of the line segment joining the points x1 fx1 and x2 fx2. For example, if this is the location of say x1 fx1 and this is the location of x2 fx2, then slope of this line has absolute value less than or equals to the Lipschitz constant capital K. In fact, we see that you consider any second line on the graph of the function y equals to fx, say this second line or this second line or whatsoever second line you consider, all these second lines are having slope in between the slope of this line which is k and the slope of this line which is equal to minus k. So slope of any second line on the graph of a Lipschitz function lies in between minus k and k. This is for a function of one variable. For a function of several variables, we consider this expression, and this expression signifies average value change of the function due to the movement from x1 to x2. If this average value change for every pair of points x1 x2 inside the set capital S is bounded, then the function f is a Lipschitz function, and hence a Lipschitz function also does not allow a sudden rapid change of the function value. Otherwise, this average value change will be unbounded and then will not let the function f to become a Lipschitz function. Let us now consider a few examples on checking Lipschitz continuity of the given expressions as follows. Let us consider the function say fx is equal to x squared on the set capital S is say the closed and bounded interval 0 to 1. Let us try to check whether this function f is a Lipschitz function on the set capital S. In order to check the Lipschitz continuity, we go for computing the supremum value of the expression fx1 fx2, their difference and absolute value in the numerator, and in the denominator we take x1 minus x2 its modulus. The supremum of this ratio for x1 x2 belonging to the set capital S and x1 is not equals to x2 gives us identical to supremum over x1 x2 belonging to S of the expression modulus of x1 plus x2, which is obviously equals to 2, and hence the function f is Lipschitz continuous on the set capital S. Now here, instead of considering this closed and bounded interval 0 to 1, if we would have considered an unbounded interval or say the entire real number line, then we see that the supremum will not be a finite quantity and therefore the function f is not Lipschitz on the set of all real numbers. In fact, from the graph of fx equals to x square, we can quickly figure out that the function is not Lipschitz continuous on the set of all real numbers. This is due to the fact that if we just draw the graph of y is equal to x square, then we see that for any positive k, the line y is equal to kx will certainly intersect the graph of y is equal to fx at the point k square, and hence we will not have any positive k for which the graph of the function fx equals to x square will be below this upside of the double cone, and hence the function fx equals to x square cannot be a Lipschitz continuous function on the set of all real numbers. From this geometrical observation, we can also quickly figure out that the function fx is equal to under root of x is not Lipschitz continuous on the closed and bounded interval 0 to 1, because simply you draw the graph of this function and you will find that for any positive k, the line y equals to kx will certainly intersect the graph of y equals to under root x. So you will not have any value of k for which the graph of the function y equals to under root x will be below the graph of the line y equals to kx, and hence the function f is not a Lipschitz continuous function on the closed and bounded interval 0 to 1, or in fact you consider any interval containing 0 to any positive a, and you will find that the function fx is not Lipschitz continuous. This is a geometrical way of sensing whether a given function of one variable is Lipschitz continuous or not. In order to prove it algebraically, you consider supremum over the given interval of the expression this ratio, which is obviously bigger than or equals to the supremum over the interval 0 to 1 of the expression this ratio, which is equal to supremum of 1 over under root x, which is equal to positive infinity, and hence the function f is not a Lipschitz continuous function. This example also gives us an example which is uniform continuous but not Lipschitz continuous. We got to know that every Lipschitz continuous function is uniform continuous, but this example indicates that not every uniform continuous function is a Lipschitz continuous function. You please figure out why this function f is an uniform continuous function on this given interval 0 to 1. Now we see that Lipschitz continuity of a function of one variable is broadly related with the supremum is a finite and definite quantity or not. Now if we have a function of one variable that is differentiable on an interval say capital I, such that the function f is differentiable and the derivative values are bounded by some constant say capital M, then the function f must be a Lipschitz continuous function on the given interval capital I. This is due to the fact that if we try to compute the supremum of this ratio over the given interval capital I, then by the Lagrange's mean value theorem, as the function f is differentiable on capital I, the expression in the numerator inside this absolute value gives us x1 minus x2 times f dash xi for some xi lying in between, strictly in between x1 and x2, and then ultimately this ratio is bounded by this constant capital M. and hence the function f is a Lipschitz continuous function on the set capital I. From all this analysis, we also can identify that if a function f is Lipschitz and differentiable, then the derivative value of the function must be bounded by the Lipschitz constant capital K. Here I would like to ask you a question, that can we have a Lipschitz function that is not differentiable? You please try to find out if such an example can be possible. Now I will end up this lecture by mentioning a surprising and remarkable result on differentiability of a Lipschitz function, which is the famous Rademacher theorem that says that a Lipschitz function is differentiable almost everywhere. This notion of almost everywhere and all, they are concepts from measure theory. I'll just state the result. If you are not interested on measure theory or on abstract mathematics, you may please just forget about it. The Rademacher theorem states that if we are given an open subset of Rn, say the set capital S, and if be a Lipschitz continuous function of n variables on the set capital S, then the function f must be differentiable almost everywhere on the set capital S. For a proof of this result, you may please visit the proof of the theorem 3.2 on page 103 of the book entitled Measure Theory and Fine properties of functions by Evans and Gary. Although in our course we will never use this Rademacher theorem, but stated here this result keeping in mind that some of you might take abstract optimization or non-smooth optimization as your research career. If you are taking up non-smooth optimization or abstract optimization as your research career, I would like to state another remarkable and fascinating result on convex analysis that says that convex functions are twice differentiable almost everywhere, and this is the famous Alexander-Ross theorem. For a neat statement and the proof of Alexander-Ross theorem, you please visit the page number 273 and the theorem 6.9 on the same book that I have written over here. Now with this I stop this lecture here, but before stopping, as I usually give a few problems to work out, let me give you to check that the function say fx is equal to x sine 1 upon x for x not equals to 0 and 0 when x equals to 0. This function is uniformly continuous on the closed and bounded interval 0 to 1. You please also try to check if the function fx is equal to natural logarithm x uniformly continuous on the unbounded interval say a to infinity for some given a greater than 0. For Lipschitz continuity, please check if the function fx is equal to 1 over 1 plus x square is Lipschitz continuous on the entire real number set. The last question that I would like to give is that consider a function of one variable that satisfies this relation fx plus y is equal to fx plus fy for all xy belonging to R, and the function f is continuous at least at a point say a in the real number set, then show that f is uniformly continuous. With this, I stop this lecture here. In the next lecture, we will consider to discuss the notion of derivative for functions of several variables. Thank you all for all of your kind attention.